So, in the last lecture we discussed about the degree of freedom. We have said that it is the number of independent displacement coordinates which can express the significant contribution of inertia forces in the given system. We have also very clearly said it is not the points where the mass is lumped, because we have shown couple of examples where the mass can be lumped still at one point, but the structure can have more than one degree of freedom, for example a TLP, for example a triceratop, etc. So, it is number of independent displacement components that will explain the significant contribution of inertia force. Since we said degree of freedom is associated with inertia and inertia is coupled with mass, therefore we said how to discretize mass. So, we said that mass can be either continuous or it can be lumped. Now, the moment I say mass can be continuous, the problem becomes slightly complicated, because then we all know that load is a function of time because it is dynamic, as well as the inertia forces which is caused from the continuous mass will also vary with the span of the member. So, there will be two variables now if you take a continuous mass system. One will be the load varying along the span or along the length of the member, because mass is not lumped at one point, but it is continuously spread for the entire length of the member. The second variable, of course, the load will vary with respect to time. So, once I have two variables in the given system, then I should go for partial differential equation to explain the motion, equation of motion. So, this is complicated, that is why we generally say the lumped mass discretization is a simplified procedure. That is the reason, because here one of the component which is varying along its length, for example this, is eliminated. We have said that the mass is lumped only at specific discrete points, therefore the variation of load along the length is eliminated from the discussion. We will only look for the time variant of the load, which is purely of course dynamic in nature, therefore the analysis can become simple. So, when you have a lumped mass system, then the analysis is simpler compared to the continuous mass system. Now, let us quickly look at what are the essential characteristics of dynamic loading. We already said that in the last lecture. Just to recap, essential characteristics of a dynamic loading. Foremost, the load will vary with respect to time. So, it is going to be time variant. As we understand the load is time variant, the response will also be time variant. Hence, like static analysis, dynamic analysis do not have a single solution, okay, it is time variant. Because it will be a function of time, x, the response will be time variant. So, that is one important characteristic of a dynamic loading. The second important characteristic of a dynamic loading will be coming from the system. The system should have significant inertia component. What do you mean by this? It explains like this. We already know the inertia force is simply given by mass into acceleration. If I take x as function of time as response of the system, I can say the inertia force can be mass into acceleration of the system. There are two components here. So, if the mass is significant, which will make the inertia force or the inertia component significant, I must do dynamic analysis. Alternatively, if the response is negligible, that is x of t is not varying significantly, variation is there, but it is not significantly varying. So, what we say is crudely the system has slow response. The system has slow response, even though mass of the system may be predominantly high, we need not have to do dynamic analysis. Okay, there is no need to do dynamic analysis. So, we are not explicitly saying mass of the system should be significant, we are saying the inertia component of the structural system should be significant, which is having two components within itself. One is the mass, of course, other is acceleration at which mass is moving. So, if you have the time variant of the response or the acceleration is not varying much significantly with respect to time, we may not do a dynamic analysis. A classical example may be, let us say, dikes or coastal protection structures which are massive, but they are fixed to the sea floor or they are fixed to the bed. Therefore, there is no need that we have to do dynamic analysis for them, because the variation of the response of the system in respect to time domain may not be significant, it will be there, but not significant. Okay. So, in that way people resolve to what we call quasi static analysis or simple static analysis as an approximate method. So, these two are considered to be essential characteristics of a dynamic loading. Any questions here? We move on further. Now, I want to mathematically model a given system to do dynamic analysis. So, the moment I say I want to do a mathematical modeling, of a given system for doing dynamic analysis, then I have to make certain idealizations, what we call as structural assumptions. The first idealization what I will start with the dynamic analysis is, I will pick up a system which is having only one degree of displacement, what we call single degree freedom system. Or in brief SDOF models. So, we will again recollect that degree of freedom is independent coordinate explaining the inertia component in a given system, and it is not the point where the mass is lumped. So, it is talking about the displacement, independent displacement components. So, in a single degree of freedom system I must restrain the motion of the mass in only one displacement coordinate. Okay. So, how do we do that, and what are the basic features of a single degree mathematical model? a single degree freedom system has essential features or essential characteristics of a single degree freedom system. I am referring this as SDOF, this is single degree of freedom. So, classically a single degree freedom system will look like this. I have a mass component, I do not want this mass component to move in the vertical direction, I am putting a constraint. So, you may wonder, if I am putting the mass component exactly resting on the floor, then there will be some resistance created by this mass component by the friction of the floor. So, I want to make it easy. So, let us say I put a wheel here and enable the mass to move only in this direction, of course to and fro. Okay. Now, as long as you do not connect this mass to any of my fixed support system, the mass will be infinitely keep on moving and I will not get what we call as a vibration. Okay. So, I want to connect this mass with the support using some component, and I also want to represent the effect of the friction generated by this mass while moving by some ideology. I put another component. Now, above all, if the whole system is in position, the mass will not activate or initiate to move at all. So, I need some external force at least to start the movement of the mass. So, I apply that and call that of course as function of time, which is a dynamic problem. And once the mass starts moving, I should be able to measure the response of the mass. I am interested in measuring the response of the mass. Since the mass is continuously moving, I should measure the response with reference to certain datum. I take the datum as Cg of the mass itself and say, with respect to this point, I will measure the response of the mass, call that also as function of time, because we just now saw in a given system which is essentially dynamic in nature, when the force is time varying, the response accounted by the inertia component or the mass component of this will also be time varying. I am measuring x of t. Now, in the whole exercise, this is an idealized model of a single degree freedom. Now, you may wonder that how this is a single degree freedom system. Look this problem from the front face of the board, you will see the mass is moving in this direction, so it is 1 degree, but where is the guarantee that the mass is not moving normal to the board? You are looking from the board side here, you are able to see the movement of the mass here, but where is the guarantee the mass is not moving the normal side? So, let us look at the view of the whole problem in this angle. So, when look at this in this angle, I will again plot the mass like this. It is a 3-dimensional model, let us say. The surface what I am hatching here is the surface what I am marking here. And the wheels what I see here, I am just trying to mark slightly in a different manner, just to make you to understand that these two views are not same. And of course, this is the floor, it is as same as this floor, and I will not see anything else because these are all hidden behind, I do not see anything of them, right. When I see from here, I am imposing an additional constraint to this mass, saying that the mass not moving anywhere in this direction. Is it clear? So, if you put a mass locked between these two surfaces and of course resting on this surface by a wheel and try to pull the mass this way now, the mass will move only in this direction. Okay. On the other hand, if you see this from this view parallel to the board, the mass will now enable movement only in this direction, which I have shown here, and the mass will not have any opportunity or any liberty or any freedom to move in the direction normal to x of t. Okay. Is there a possibility the mass can jump? Is there a possibility the mass can jump? We are assuming that the mass is integrally connected through a wheel and resting here, and we gently apply this force only purely in the direction of motion of what we are measuring. There is a possibility that if you apply this force angular and try to lift the mass and release, the mass may jump. Okay. So, the direction of motion of the force, application of force is exactly in the direction of motion of the body. So, the mass is now made to move only in one direction ideally, okay. In other direction it is restrained. Now, single degree of freedom therefore is an idealized model of single degree of freedom is therefore an idealized model. The moment I say model, it is not a physical model, it is a mathematical model. Okay. It is an idealized model where the displacement except in one direction or is whatever may be constrained. This constraint is imposed by me. I am imposing this constraint. Okay, it is not existing, I am imposing this constraint. Why I am imposing this constraint? Because I want to be sure that the mass will move or get displaced only in one direction. But in general, if you have any system like this, mass will have freedom to move in any direction the mass wants. So, single degree of freedom are those mathematical models which impose constraint to displacement directions in all other degree except one of your choice. That one can be translational, one can be rotational also, but only one, not necessarily translational, it can be rotational also. It means how many such idealized mathematical models in single degree freedom system exist in the literature? Is the only model exist or any other models exist? Before we see those respective models which exist in the literature which impose constraint on any other degree or direction of motion except one, we will first understand what are my essential characteristics of this idealized model and what actually do they represent in physical terms, because they are important for me to solve the problem. Okay. Any questions here? Any doubt, any questions here? We will remove this. If you look at this figure which I have drawn, I will call this as figure 1 and let us say figure 2. If you look at figure 1, mass represented by m indicates presence of inertia force in the system. Okay. the spring attached to the mass here having some stiffness. Let me put that stiffness as K. So, actually it is not stiffening the movement of the mass, it is implementing an elastic restoring force. It is restoring the force. What does it mean is, when the mass is made to move towards right, the spring attempts to bring the mass back to its position. When the mass is made to move to the left, the spring pushes the mass to the right or to its initial position. It means it is restoring the original position of the mass and it remains elastic. It means this element will not impose a permanent deformation or displacement to the mass. Okay. This is what we call as represented by stiffness, indicated by letter K, unit be Newton per meter, and unit will be, in this case mass units will be in kg. When you try to move the mass towards right, the spring tries to bring the mass to its left, it restores the position of the mass. Now, when this mass is being moved to and fro, there is a probability that in addition to the force exerted by the restoring component, the movement of the mass is also attempted to be depleted or stopped by a friction generated between the wheel and the surface. Okay. So, there is some dissipation of energy or a friction force which is applied to this mass, that is indicated by a damping component which is indicated by C. There are many models about damping, we will talk about that later. It can be velocity proportional and so on, we will talk about that later. So, the first component of an essential characteristic of single degree will be mass, second will be stiffness, third will be damping, and of course fourth will be the excitation force indicated by f of t, which is a function of time. Now, the question comes, if these are all essential characteristics of single degree of freedom system, do we need all of them? Do we need all of them to be present all the time? I mean, all the time you want m to be present, k to be present, c to be present and f of t to be present. So, literature in dynamics classifies them slightly in a different manner. They say the method by which you want to do the analysis, accordingly you can say that which should be present, which should be absent. So, let us say this is element, or now we talk about the responses, because I am interested about the responses of the mass for a given loading. The responses can be categorically divided. The response can be undamped, free vibration. That is one category of the response. The second can be damped, free vibration. The third category can be undamped forced vibration. The fourth can be damped forced vibration. Now, how do we understand them symbolically? Let us say my contents which are present V will be mass, stiffness, damping and F of t. This is what I have. So, if I try to see which will be present and which will be absent under this category, we can quickly make a matrix to understand this. For doing a dynamic analysis, the essential characteristic of dynamic analysis is it should show significant presence of inertia component. Inertia component generates from mass. In all category, whether you do analysis in any format, you must have mass present in the format. The mass should be connected to my support system to restore its position to its normalcy. The restoration can be done by two ways. One can have an elastic restoring component present in the system, can also model the friction present in the system as a damper. Okay. Now, there is an option. If you have got two options, can one have at least one of them in the system. So, the basic model says always have the elastic restoring component in your analysis. It should be always present. Okay. Now comes undamped. So, damping is not there, undamped damping is not there, damped damping is present, damped damping is present. You may wonder that if you do not have f of t, which is a function of time, which is acting externally on the body, how will I apply dynamic analysis to this body? Because essential characteristic of dynamic loading is force should be time variant and inertia component should be significantly present in the system. So, we have proved the second one, inertia is significantly present in the system, but do we have to say that f of t will be always present in all the cases? Now, there is a classical difference here in dynamic analysis. People say do what we call free vibration. What does it mean is you apply the force initially and then release the force instantaneously. So, you have to activate the movement of the mass. The force may not be present always. Now, the question here what I am asking is, do all of them to be present at all the time? That is the question what I am asking. I am trying to answer this matrix. The moment I see free vibration, I need not have f of t present all the time. The moment I say forced vibration, I want f of t to be present all the time. So, you may please do not get confused that if f of t is not there, how the body or the mass will actually get excited. The question here asked is, do I need f of t to be present all the time during the analysis? That is the question asked. So, initially you want f of t to start the motion of the mass, then you stop applying f of t to the system, the mass will keep on vibrating at its own characteristics. So, the response analysis for a single degree of freedom system has got 4 classifications: undamped free, which we will see first, then damped free, then undamped force and damped force, same order. So, this will give me a clue which components will be present and which components will be absent in my analysis. So, the name itself can give me a clue, or when you look at any literature or any paper which talks about free vibration etc., it is understood that f of t is not there. Remember, all of them are essential characteristics of a idealized single degree freedom system model as we see here, but dynamic analysis classify them into a matrix like this. Now, why this has been done? What is the necessity for doing this classification? Why we should do this? Why it is to be necessary that this classification or the study on dynamic analysis response of a single degree should be done in 4 different analogies. What is the necessity? Any idea? Because that is a very important question. If you do not understand the reason why, natural frequency can be calculated in, do you mean to say it can be calculated in all the analogies? Is it necessary? Because we have not spoke about the natural frequency yet, because when the body vibrates it is vibrating a specific frequency. We are going to speak about that in the next component of the lecture. So, natural frequency, what he is trying to say is the analogy is there because I want to estimate the natural frequency of the vibration of the given system, therefore I need it. That may not be the right answer. There is a very important categorical understanding and compulsion why I have to divide this into different components, very important. Let us try to understand this, then we will move forward. Let us talk about f of t. The moment I say forcing function is varying with time, it will be a oscillatory motion or a vibratory motion. Okay, the force will also be oscillatory. The moment I say oscillatory, this will have a specific frequency at which it is vibrating. Suppose I eliminate this in my study, I will not see the influence of the forcing frequency on the natural frequency of the model. Suppose if we include this in my study, I will know the influence of the forcing frequency on the natural frequency of the model. So, distinctly f of t present, f of t absent has got a very distinct meaning in the dynamic analysis. Talk about damping, because we talk about undamped and damped systems. If we eliminate damping, you are not including any loss in the material or in the displacement caused to the mass, either because of friction or because of content of air or environment present in the system. If you include damping, you will know the influence of this on the response. How do you know that? Exclude damping, get the response, include damping, get the response, compare them, you will know what is the influence of damping on the response. So, damped, undamped will have a significant understanding in the classification of dynamic analysis like this. Now, I have a question, why stiffness should be always present in my model? Sorry, it will restore.
Rigid body cannot vibrate. So, property of the material.
No, let us answer one by one quickly. He says rigid body cannot vibrate, but I am asking about why stiffness should be there. Rigid body cannot vibrate, then the rigid body is remaining static, no dynamic analysis to be done, because I already said when x of t is not significantly varying, then there is no need to do a dynamic analysis. So, rigid body means it has to vibrate, then only dynamic analysis is important for me. So, that question is, that answer maybe it is ruled out. Any other answer?
Is a property of the material which cannot be excluded.
You mean to say the stiffness is a characteristic of the material? It is an elastic restoring force present in the system. It may not come from the mass component, it can come from some other supporting component of the system also, we do not know that. Because of the body is vibrating. Suppose I eliminate K and give C only, still also the body will vibrate.
The body will not vibrate if K is excluded.
If the restoring force is removed, I have a damper. You understand how does it work? This symbol, how does it work? It is very simple to understand. I have a cylinder, let us say a piston, this is a fluid, insert this, when I am connecting this to a separate piece and this to a separate piece, the relative motion between these two will be controlled by this fluid inside. No, no, not necessarily. Not necessarily. It will not be equal to Ft. Not necessarily it can be equal to Ft. This will also restore, this will also bring back, because the fluid will have a capacity to bring back its motion or damp the motion. Okay, for example, do not try to imagine you are pulling the body, you are pushing the body. Okay, it will cause vibration.
So for harmonic motion,
No, it is not depending upon the characteristics of the motion at all.
Then we cannot analyze the natural frequency of the system. If
Why?
Sir, if only damper will be there, then it cannot means vibrate in the natural system, natural frequency.
You mean to say it will vibrate in a different frequency?
Sir,
Or it will not vibrate at all?
No, sir. It can vibrate, but
Yeah.
slowly its frequency can change.
That is fine, but because it will vibrate at specific frequency called omega d, which you call damp frequency, we are not talking about that here. Fine, frequency will change, but once frequency is there, it is vibrating. But there is a basic problem with this. Talk about this elasticity. I am talking this as elastic restoring force. Will this guarantee an elastic restoration? It will not. Okay, restoration may be there. What does it mean? At any given point of time, damper cannot ensure return of mass to the original position at all. That is what elastic is or non-elastic is. It will create a permanent displacement to the mass. I will never know what was the initial position of the mass after lapse of time capital T. Whereas elastic means it will restore the mass even after infinite time, expected to restore the mass at the original level of reference or frame of reference. So therefore, K or the component of stiffness which is indicating elastic restoring force in a given system should always be present for an analysis. Adding to this, when you have only the damper and not K, then obviously the damped frequency will be different from the natural frequency, therefore we cannot capture the natural frequency of vibration of the given mass. Agreed? Okay. So each one of these distinct divisions in dynamic analysis have very interesting consequential meaning, why they have been divided. Okay. Now the question comes, what are those idealized single degree of freedom systems where only one direction of displacement is imposed on the system, remaining all are constrained? One simple example is spring mass system. This is a single simple example of spring mass system. I am not putting a spring mass dashpot system. Now this can move only in one direction as we saw there. The second can be a torsional pendulum. So at any given point of time, the pendulum will have rotation theta, which can be moved to the vertical axis. I think you people have something very different or anything to share. You both, please leave the class. Before attending next class, you come and meet me. 1 and 2 both you, please leave the class. If you do not leave, I will stop the lecture. Before attending, come and meet me personally. because I think we are teaching to people who wanted to learn. We do not want to teach people who are Einsteins born, right. If any Einsteins are born here, please leave the hall. You can disconnect and discontinue with the course. I am not interested. Okay, we will stop the lecture today. We will see tomorrow, next class.